Hello everyone, in today's video we will understand the groups in mathematics. In this session we will explore the fundamental concept of groups which serve as a foundation for various algebraic structures. First we will understand what is group theory in mathematics. Next the definition of group. Along with that we will see the properties of group. And next we will prove a simple theorem using these axioms. After which we will see the applications of group. And finally we will end the session by looking after the university question. Now first, what is group theory in mathematics? Group theory is a branch of mathematics that deals with study of groups, which are algebraic structures consisting of a set of elements and a binary operation defined on that set. In group theory, mathematicians analyze the properties and symmetries of these groups, which can be used to understand the various mathematical structures as well as the symmetrical patterns and transformations in different contexts. To be more concise, group theory is a branch of abstract algebra that focuses on study of groups, which are algebraic structure consisting of a set and a binary operation defined on that set. And now let's see some mathematical concepts and their relevance to group theory. First, subgroups. Subgroups are subset of a larger group that themselves forms a group. And they are essential in understanding the structure of groups. And next, cyclic groups. Cyclic groups are groups generated by a single element. And they help in studying the algebraic structure which are relevant in group theory. Permutation groups deals with the symmetries and rearrangement of finite sets, as they are important in combinatorics and group theory. Lagrange's theorem. Lagrange's theorem provides a fundamental relationship between the order of subgroups and order of parent group, crucial for group analysis. Next, isomorphism. It relates two groups that have same structural properties even if their elements are different. It's a way to establish group equivalence. And then we have homomorphism and automorphisms. Homomorphisms are structure-preserving mappings between groups, while automorphisms are special homomorphisms with a single group. And they help understand group transformation. Next up, Galois theory. Galois theory connects the group theory with the field theory, and it is used to study the solvability of polynomial equations. And it has applications in algebra and algebraic geometry. Next, we will see the definition of group. A group is a mathematical structure that consists of a non-empty set G and a binary operation defined on G. The binary operation is often denoted as asterisk. And here is the formal definition for group. A group is an algebraic structure consisting of non-empty set G and binary operation asterisk defined on G and satisfying the four properties called group axioms. The four fundamental properties are closure property, associativity, identity element E, and inverse element. These four properties collectively define the algebraic structure known as group. If a set, an operation, and these four properties are satisfied, then that structure is considered as a group. Groups have numerous applications in mathematics, physics, computer science, and many other fields, and they play an important role in understanding the symmetry, transformations, and various mathematical structures. Now let's delve into the properties of group. So before getting into the properties of group, let's define what is set and binary operation. The term set is a general mathematical concept that refers to a well-defined collection of distinct objects considered as a single entity. Sets can contain elements of various types, and they are not limited to the context of group theory. For instance, we can have a set of numbers, a set of letters, or set of anything else. In group theory, set G represents the collection of elements over which the group operation is defined, and it is a fundamental component of group structure. So set G specifically refers to the underlying set of elements that form a particular group. So we can say set G is like group's toolbox containing all the elements it needs to perform its mathematical operations and define its properties. The terms set and set G are related but refer to the different things within the context of mathematics and group theory. And here is a formal notation of set G. So in the context of group theory, set G refers to the set of elements that forms a group. In other words, G is a set of all elements that can be combined using the group operation to produce the other element in the set and that satisfy the group axioms. The group axioms are set of properties that define what it means to be a group. In formal notation, it can be represented as set G equals elements of G. Here, set G is set in the group theory, and elements of set G represents the collection of elements contained within the set G. In simple terms, set G refers to a set. The part within the curly braces lists the individual elements that belongs to the set. And next, binary operation. In group theory, a binary operation is denoted by asterisk, which is a mathematical operation that takes two elements from the set and then combines them to produce a single element. A binary operation is one of the key components used to define a group. Mathematically, it can be represented as A star B equals C. Here A, B, C are the elements of set G. The asterisk is the binary operation defined on the group. C is the result of applying the binary operation asterisk to the elements A and B. The binary operations can take various forms such as addition, multiplication, composition, or any other operation defined on the set depending on the context. The formal definition of binary operation on set G is given here. For a set G and binary operation, we say that is a binary operation on G if for every pair of elements A and B in G, the result of the operation A star B is also known as element of G. It states that a binary operation asterisk to be considered as a binary operation on G, it must satisfy the following condition. That is, for every pair of elements A and B in the set G, the result of the operation A asterisk B must also be an element of set G. And this condition ensures that the operation combines the elements from set G and produces a result that remains within the same set G. Now let's see an example of binary operation on a set. In this example, G is a set of even integers. Asterisk represents multiplication. Now let's check if asterisk is a binary operation on G based on the definition. That is, for every pair of element A and B in the set G, the result of the operation A asterisk B must also be an element of set G. Let's test it. Take two even integers from G. Let's take A equals 2 and B equals 4. On multiplying A and B, we get 8. Since 8 is also an even integer, it belongs to G. And the condition is satisfied. Let's do this again. Take two even integers from G. For example, A equals minus 4 and B equals 0. On multiplying A and B, we get 0. Again, 0 is an even integer. It belongs to G. So the condition is met. Now let's move to the core topic, properties of group. And these properties are a set of fundamental characteristics that a group must satisfy. There are four primary properties that define a group. First, we have closure property, associativity, identity element, and inverse element. First, closure property. For all elements A and B in the group, the result of the group operation, that is A star B, must also be an element of the group. In other words, combining any two elements of the group using the group operation must yield an element that is still within the group. The mathematical statement for the closure property is given here. Let's see an example. Here we have a set of positive integers. Also we have a binary operation defined on the group. Here the operation is addition. Now take two positive integers, 2 and 3, and both the elements belong to the group G. So in this case, when you add 2 and 3 using the addition operation, you get 5 as a result. The closure property is satisfied because the result 5 is also the positive integer and it belongs to the same group G, which consists of positive integers. So if you add any two positive integers together, the result will still be a positive integer. And this demonstrates the closure property that the group is closed under addition. The closure property is a combining rule. Next, associativity. The group operation must be associative. This means for all elements A, B, and C in the group, the following equality holds. A star B star C equals A star B star C. This property implies that when you perform a group operation on three elements A, B, and C, it doesn't matter how you choose to group them. Whether you first combine A and B and then combine the result with C, or if you combine B and C first and then combine the result with A, you will always get the same result. In simple terms, the order in which you apply the group operation does not affect the outcome. And this property ensures the group operation is consistent and well behaved. The mathematical statement for this property is given here. Now let's see an example on this property. Consider three positive integers 1, 2 and 3. Here we are using addition. In both cases, when you add these positive integers, you consistently get the result of 6. And this demonstrates the associativity property, which states that grouping of elements doesn't affect the final result when the addition is applied. Now let's see the identity element. In this property, there exists a unique element E in the group G known as the identity element. This element has a special property, that is, when you combine or operate any element A from the group with the identity element E, the result is always the same element A itself. The mathematical statement for this property is given here. Let's see an example on this property. We have a group set with positive integers. In this group, the identity element is 0. Here the operation is addition. When you add 0 to any positive integer, it doesn't change the positive integer. In first case, we are adding 0 to 3 and it doesn't change 3. In second case, we are adding 3 to 0 and this also doesn't change 3. And the identity element 0 serves as a do-nothing element. In other words, the identity element serves as a neutral element with respect to the group operation. Next up, we have inverse element, and this property states that for each element A in the group, there exists a unique element A inverse within the same group, and the combination of A and its inverse results in the identity element of the group. The mathematical statement for this property is given here. Here A is any element in the group G. A inverse is a unique inverse element within the group G, and E is identity element. In simple terms, every element in the group has an element within the same group that can undo its effect when it is combined to the group operation. Let's see an example. Here we have group set with positive integers, and we're going to add two positive integers. For the positive integer 4, it has the inverse minus 4. On adding positive 4 and negative 4, we get 0. And this example illustrates how the negative integer serves as the inverses of positive integer with respect to addition. Now let's see a simple theorem. This is a straightforward theorem and proof that illustrates the property of identity element in a group. The theorem states that in any group, the product of any element with the identity element is equal to the element itself. Before we dive into the proof, let's outline this approach. First, we will start by defining a group and its identity element. Then we will show how this identity element interacts with the arbitrary element within the group. In step 1, we begin by defining our group, and it is called as G. Within the group, there is a special element called identity element, which is represented by E. In step 2, we will take any element from our group G, and here we take an element A. Keep in mind, A could be any element within our group. And next, the step 3. This is where the magic happens. We are going to show how A interacts with the identity element E. By the definition of identity element, we have the equation A asterisk E equals A. And this means when we combine A with E using the group operation, we get A itself. And this is left identity property. But we are not done. In step 4, we will also consider the right identity property, where we will show E asterisk A equals A. And it's a crucial part of the proof. Now let's consider a right identity property. Again, we are in the group G with an identity element E, and we have element A. Using the definition of identity element, we see that E asterisk A is also equal to A. This confirms that when we combine E with A on the right, we get A as a result. E is a do-nothing element. When we introduce E to A remains unchanged. And we have demonstrated left and right identity properties. This proves the identity element property in the group. It shows that when you combine any element A with the identity element E, you get back the original element A as stated in the theorem. Next, let's see the applications of group. Symmetry and group actions play a significant role in application of group theory to study the discrete objects like graphs. Group theory plays a vital role in modern cryptography. Public key cryptography schemes like Diffie-Hellman key exchange and RSA algorithm rely on the mathematical properties of certain groups, particularly in modular arithmetic to secure communication and data. In information theory and coding theory, groups are used to design error correction codes and analyze their properties. Group theory concepts are employed in number theory to study the properties of integers and modular arithmetic. Concepts like residue classes and congruences can be expressed algebraically using group theory. Groups are the foundation for more complex algebraic structures like rings, fields, and vector spaces. And understanding groups is crucial for comprehending these larger algebraic systems. Group theory is used to study the combinatorial objects and structures. It helps in analyzing the symmetries of various combinatorial configurations such as graphs, polyominoes, and designs. In robotics and computer graphics, objects in 3D space can be transformed and moved using various operations like translation, rotation, and scaling. And these operations can be represented as group actions, which help in understanding how these transformations combine and interact. Group theory provides a powerful framework for understanding the solvability of polynomial equations by analyzing the symmetries of their roots. And it helps in determining whether an equation can be solved using the combination of addition, subtraction, multiplication, division, and root extractions. These are just a few examples and applications of group theory. AI continues to advance and its applications are expanding into new domains. And so far we have seen the applications of group theory. Now let's see the university question. Here we need to demonstrate that the set of integers z under the operation asterisk defined as a asterisk b equals a plus b plus 1 forms a group. Now let's understand the question. This notation z asterisk refers to the mathematical structure where z represents the set of integers and asterisk represents the binary operation defined on this set. If the group is a part asking you to prove that the combination of the set z and the operation asterisk forms a group, where is defined by a asterisk b equals a plus b plus 1. This specifies how the binary operation asterisk is defined. In this case, a asterisk b is defined as a plus b plus 1. So the statement is asking you to prove that when you take a set of integers z and use the operation asterisk defined as a plus b plus 1 for any two integers a and b, the resulting structure must satisfy all the criteria of a group. This includes showing that it is closed under the operation, associative, has an identity element, and has inverses for each element. Now let's see whether it satisfies the four fundamental properties of group. First, the closure property. Closure is one of the most fundamental properties required for a set and operation to form a group. So for all a, b in z, the result of a asterisk b must also be in z. Let's take two arbitrary integers a and b from z, and when you perform the operation a asterisk b by adding a and b and then adding 1, the result is still an integer. So when you add two integers, the result is always another integer. Now let's see an example. Take two integers from z. For example, a equals 2 and b equals 3. To check closure, we need to see if a asterisk b is still an integer. And in this case, on multiplying a and b, we get 6, which is still an integer. Now perform the operation. To confirm the closure, we need to ensure the result is also an integer. Now add the values of a, b with 1 and we get the result 6. And it shows that the operation maintains the closure for the set of integers z as the result of the operation is an integer. So the closure is satisfied. Now let's check the associativity property for the operation asterisk defined as a plus b plus 1 is correct. For this, take three arbitrary integers a, b, c from the set z, and we need to show that a asterisk b asterisk c is equal to a asterisk b asterisk c. Let's begin with the left hand side of the property. We need to simplify the expression inside the parenthesis. So we will take a asterisk b. We replace a asterisk b as a plus b plus 1. And now we have a plus b plus 1 asterisk c. Here a plus b plus 1 is a and c is b. Again compute a asterisk b as a plus b plus 1. So we have a plus b plus 1 plus c plus 1. Now adding the result, we get a plus b plus c plus 2. Now let's prove for the right hand side. Now start with the expression b star c, which is defined as b plus c plus 1. Now calculate b plus c plus 1. Distribute the operation a into b plus c plus 1. Here a is a and b is b plus c plus 1. Now we have in the format a asterisk b. We have to write it as a asterisk b equals a plus b plus 1, which is given in our sum. So we rewrite the expression as a plus b plus c plus 1 plus 1. Here a is a and b is b plus c plus 1, and for 1 there is 1. And finally we simply combine the terms so that we get a plus b plus c plus 2. Since in both expressions we have a plus b plus c plus 2, so the associativity property is met. Now let's provide values and evaluate the expression and see whether they are equal. Let's take specific values for a, b and c. For example, take a equals 2, b equals 3 and c equals 4. Now we can evaluate both sides of the associative property. For left side, substitute the corresponding values for a, b and c. And similarly, substitute the values for a, b, c on the right hand side. The both side values are equal and it confirms the associativity property for the operation asterisk defined as a asterisk b equals a plus b plus 1. Now let's see the identity property. The identity property states that there exists an element in the group called identity element. When the identity element is multiplied with any other element in the group, the result is the other element itself. In mathematical notation, it can be expressed as a asterisk e equals a, e asterisk a equals a. Okay, using the definition of multiplication, let's see e satisfy the equations. From the definition, we have a asterisk b equals a plus b plus 1. So for the equation a asterisk e equals a, we have a equals e and b equals a. And for the equation e asterisk a equals a, we have a as a and b as e. On performing the operation on both equations, we get a plus e plus 1 equals a as first equation and e plus a plus 1 equals a as second equation. Now add both the equations. From that we get 2a plus 2e plus 2 equals 2a. Now bring 2a to the left hand side. So plus 2a becomes minus 2a. We can cancel plus 2a and minus 2a, after which we will have 2e plus 2 equals 0. Now divide this equation by 2. So we get e plus 1 equals 0. Taking plus 1 to the right hand side, we get minus 1. That is e equals minus 1. Now let's check minus 1 is an identity element. Now replace the value of e as minus 1 in both the equations. We get a. So for all integers a, the operation with minus 1 as the identity element satisfies the identity property. Now let's verify a with integers. Let's take a equals 5. On replacing the value 5 for a in the equation, we get 5. In both cases, we get the same answer. So the identity property holds for a equals 5. And we can check for negative integers also. And finally, we need to discuss the fourth property, inverse elements. And here we need to apply the identity property to the equation a asterisk b and b asterisk a equals e. The inverse property states that for every element a in the group, there exists a unique element called a inverse in the same group. And when you combine a and inverse element using the group's binary operation, it results in group's identity element. The mathematical expression for the inverse property is given. That is a asterisk a inverse and a inverse asterisk a equals e. A represents the element from the group. A inverse represents the unique inverse element of a. Asterisk is group's binary operation. And e is identity element of the group. Now let's apply this property to the equation. That is a asterisk b equals e and b asterisk a equals e. First a asterisk b equals e, which means when you combine an element a and b using the group operation asterisk, it results in an identity element e. And b is the inverse element of a because it undergoes the effect of a. Next b asterisk a equals e. This is similar to the first equation, but the order of a and b is reversed. And here also b is the inverse element of a. And when you combine b with a using the group operation asterisk, it should result in an identity element. It ensures that you can cancel out the effect of any element in the group by combining it with the inverse, which will result in an identity element. Now let's find the inverse element for an arbitrary integer a. First we will find for a asterisk b. A asterisk b equals a plus b plus 1 is given in our sum. So replace a asterisk b as a plus b plus 1. Now isolate b. Take a and plus 1 to the right hand side. Now we get the b value e minus a minus 1. And also check for b, which serves as inverse for a. For that, substitute b value as e minus a minus 1. And then rearrange the terms. Minus a plus a get cancelled. Also cancel plus 1 and minus 1. And finally we get e. Similarly for b star a, we get e. And you can see a asterisk b and b asterisk a gives e, which satisfies the inverse property. Now let's put some values and verify the inverse property. Let's take an integer a equals 3 and e equals minus 1 from identity element. Now we need to find the inverse element for a. Take a asterisk b equals e. Now substitute the value of a asterisk b equals a plus b plus 1 from the defined operation. And isolate b. Take a and plus 1 to the right side. And now we have b equals e minus a minus 1. Substitute the a value so that we get b equals minus 5. And this is the inverse element of a. Now let's verify with inverse property. Check for a asterisk b. Replace the value of a and b in the equation. And now we get minus 1, which is the identity element. Similarly check for b asterisk a. And here also we get minus 1, which is an identity element. Therefore we have shown that z and star forms a group under the defined operation asterisk because it satisfies the group axioms of closure, associativity, identity element and inverse element.